Welcome back, and this is the last in the series of videos looking at pH and Ka. And in this video we're going to be looking at the effect of changing the R group on the strength of the acid. We're also going to be reminding ourselves about strength of bases as well. So you're going to need your notes, and we're on page 17. So before we start, we should really consider what makes something an acid. So if we remember our definition, an acid is a proton donor. So anything which enables something to donate the proton better or not hold on to the proton as strongly will make something a stronger acid. Because if you think, remember, we've got our HA, our acid, and it will dissociate to a greater or lesser extent to release those hydrogen ions. So the more we can drive this reaction forwards, the higher the concentration of hydrogen ions, the more it dissociates, the stronger the acid. So on page 17, we're considering these acids, from ethanoic acid, which is the least acidic, it's got the highest pH, to trichloroethanoic acid, which is the lowest pH because it's the most acidic. So that one's the strongest acid. And drawing those acids out in full, we have ethanoic acid, benzoic acid, methanoic acid, chloroethanoic acid, and trichloroethanoic acid. We need to understand the effects of changing this R group on the strength of the acid, and they become stronger as you go towards this side. So first of all, let's just consider a normal acid with any R group on it. I'm going to consider, because these are all organic acids, so they're all defined as weak, but some of them are less weak than others. So if you think about what's going on in this case, you're going to have this reaction, we hope, going on as that hydrogen ion comes loose. Now in this case, we want this negative to be as low as possible, and we want this bond between the O and the H to be as weak as possible. The weaker we can make this bond, the easier it will be for the hydrogen ion to come loose. The less negative this becomes, again, the better, because then the hydrogen ion won't rejoin and this reaction won't go backwards. So those are the two things we need to consider in each of these cases. So let's consider the first three of these: ethanoic, benzoic, and methanoic acid. If we remember back to something we've studied many times before, the effect of the R group, the methyl group. Methyl groups, if we remember, are weakly electron donating. Now they will donate electrons whether you like it to or not. So in the case of ethanoic acid, you've got this R group which is weakly donating electrons. This is going to increase the electron density on that O negative, and it's going to mean that that hydrogen ion is going to be much more likely to join back on, and this reaction is likely to go backwards, or at least the equilibrium position will lie further over to the left hand side. So this equilibrium position will lie well over to this side, because whether you like it to or not, that R group is going to weakly donate electrons. Methanoic acid here, well, you don't have an R group here. So because there's no R group, there's no weakly electron donating effect, so that makes that one a stronger acid. Lastly, we need to consider the one in the middle. We need to consider benzoic acid. Now, benzoic acid, these oxygens, remember, are not directly bonded to the ring, so they can't overlap with the ring and increase the electron density of the ring, but they are electronegative, and you've got a large pool of electrons here, these delocalized electrons, which are going to be drawn out of the ring. The inductive effect, this pushing of electrons, is not as noticeable as it is here, and that's why they sit in the middle, because although the benzene ring can be electron donating, it's nowhere near as strong as a methyl group is electron donating. So that explains the first three. It's to do with the electron donating effect of the R group. This is firstly strengthening this bond because it's pushing electrons towards the OH group, and in this case it increases the electron density of the O negative, so the hydrogen ion is much more likely to reattach and the equilibrium position get pushed backwards. Okay, so the next two we're considering is chloroethanoic acid and trichloroethanoic acid, both of which are stronger than the original ethanoic acid, and this is down again to this R group. The chlorines are all quite electronegative, so they're all delta negative. So this is going to withdraw electrons or withdraw electron density from this OH group, weakening the bond between the oxygen and the hydrogen and making it more likely or more energetically favourable that the hydrogen ion can dissociate. The second reason, again, comes back to the stability of the anion that you have made. And again, same argument as before, because these are now very electron withdrawing, because you've got this delta negative, it stabilizes this anion. It's because it's withdrawing electron density. So the same in the other case, but this time I've got 3 chloro groups, each of which can slightly remove electron density from this oxygen, stabilizing this anion. So there's 2 effects going on. The delta negative group weakens this bond because it's going to pull electrons through this way, weakening this bond on the end. And secondly, once you've formed the anion, the delta negative group can stabilize it again by withdrawing electron density. Anything which withdraws electron density from the OH group, weakening the OH bond, stabilizing the anion, is going to make something a stronger acid. Next, we're going to consider the bases. So if you remember, a base is a proton acceptor. So in the first example, we looked at how to make an acid a stronger acid, and we said that anything which donates electrons makes it weaker. Because you don't want the electrons being donated onto the oxygen. That's just going to strengthen the OH bond. It's going to make it harder for that OH group to break apart, the hydrogen ion to come loose, and it's going to make that anion much less stable, much more likely for it to collect the hydrogen ion again. So anything which is electron donating is going to make it weaker. But that's for an acid. For a base, it's the exact opposite. Anything which donates electrons will make it stronger. So anything which donates electrons makes it a stronger base. Anything which donates electrons makes it a weaker acid. You have to think of these in pairs. Remember, this is why we have acid-base conjugate pairs. So an acid is a proton donor, base is a proton acceptor. So here are my 4 amines. They all act as bases, and the reason they all act as bases is they have this lone pair on the nitrogen which can accept a proton. So anything we can do to increase the electron density of that lone pair is going to make it a more effective or a stronger base. So in the first case, we have phenol amine. This is the one with the least basic. It's got the lowest pH. And the reason for that is that nitrogen's lone pair overlaps with the ring of electrons, or the ring of delocalized electrons in the benzene ring. So in this case, the electrons are going the wrong way. They're going into the ring. And that is going to weaken the electron density here. It's going to make the ring more reactive, but you can't have your cake and eat it because it's going to make that lone pair less reactive. Ammonia kind of sits in the middle. It's not got anything which is going to donate electrons, but it's also not got anything which withdraws electrons. So then we move on to methyl amine. Well, methyl amine has 1 alkyl group. We call these alkyl groups, KYL. Okay, because they're alkyl. It doesn't matter how many carbons I've got here, it only counts as 1. You've got an alkyl group, which is weakly electron donating, increasing this electron density. Dimethylamine, exactly the same argument, but you have 2 methyl groups, both weakly electron donating, both increasing the electron density of that lone pair. So we're now on page 18 of your notes, and we're looking at an exam question which caught out a lot of students when it was asked back in 2017. So it's looking at glycolic acid. So glycolic acid here, you've got your normal OH group and this extra OH group here. And they asked for a possible explanation as to why the value of Ka for glycolic acid was much higher than that of ethanoic acid. We also have two possible explanations on this page. So the most common example of a wrong answer was this first one, where they talked about the fact that there's two OH groups, therefore you get double the concentration of the hydrogen ions. Well, this one, totally wrong, no. Okay, do remember OH groups, unless it's part of a phenol group, are not acidic. So they're never going to lose the hydrogen from a normal alcohol group. The second answer was slightly better. They did mention the fact that the oxygen is electronegative, which got them a mark. What they neglected to say is that because the oxygen is electronegative, they would either withdraw electrons, therefore weakening the bond between the OH and allowing the hydrogen ion to come loose, or the fact that it would stabilise the anion once the anion was formed. So what's actually going on is this OH group here is acting like the chloro groups in the example we looked at on the previous page. It's withdrawing electrons. So that's going to do two things. It's going to weaken the bond between the oxygen and the hydrogen, meaning that hydrogen ion is much more likely to come loose, can dissociate more easily, but also it will stabilise the anion being formed. So when this hydrogen ion is lost and you have the negative on that oxygen, it stabilises it. Technically, what you actually get on that group is the delocalization of that negative charge. Looks like that. But again, same argument applies. That negative charge is reduced because of the electron withdrawing effect of that OH group. Electron density going this way reduces the electron density in this group, stabilising this anion, making the hydrogen ion much less likely to reattach. The last page of notes is basically just looking at terms and definitions, and you do need to know all of these and you need to be able to quote them. So just going through them very quickly, a Bronson-Lowry acid, which is our definition of an acid, is a proton donor. A base is a proton acceptor. They always come in these conjugate acid-base pairs, so they're always linked. You have to have a base to which to donate the proton, and you have to have an acid which has a proton to donate. A strong acid completely dissociates into ions, and that usually means it has a high concentration of hydrogen ions. A weak acid, on the other hand, only partially or slightly dissociates. Concentrated acids, and don't get concentrated and strong confused, because they are actually different concepts. Monobasic acids, monoprotic acids, quite often interchangeably used. I would try to stick to monoprotic acid, as that's one your exam would tend to like, but you will see a lot of places written as monobasic acids. They mean the same thing. Basically, they dissociate to produce one hydrogen ion, as opposed to diprotic acids like sulfuric acid, which on complete dissociation will give up two hydrogen ions. Definitions, please make sure you just write the formula. So if you're asked to define pH, this is what you write. Don't write it out in words, it's much easier to write the formula. Likewise, if you're asked to define the ionic product of water, it is this equation. You do not need to know this number, but it's helpful to remind yourself that at 25 degrees Celsius, 298 Kelvin, it's 1 times 10 to the minus 14. But do remember these are temperature sensitive, so this is only valid at this temperature. Every time you see the P there, it means take minus log to the base 10 of it. So pKw is minus log to the base 10 of Kw. So the acid dissociation constant, this is for weak acids, is this hydrogen ion concentration times the salt divided by the concentration of the HA. Now, more accurately, it is this, because these hydrogen ions, protons don't just sit around, they would join on with the water to make H3O positive. But do notice that water never appears in these Ka expressions. Well, that finishes looking at pH and Ka. There's one more pack which deals with acids and bases, and that is the buffers pack, which will be coming up shortly. So until then, take care, stay safe, bye-bye.